Lesson 7.1, solving systems of two equations. We've talked about systems of equations in Algebra 1 and Algebra 2. Most of those equations were linear. What we're going to talk about in pre-calc is finding where the intersection of linear equations occurs, but also involving quadratic and different types of functions. So in this lesson, we're going to talk about the substitution method, the graphing method, and the method of elimination, which is also known as linear combinations, and then we'll apply them to a few application problems. The solution of a system is simply an ordered pair that is a solution of each equation. So if it's going to be a solution to the system, it must satisfy or be a solution to both equations. In this first example, we want to solve the system using the substitution method. If we look at the variables x and y and look at the coefficients in front of those variables, in the first equation, the coefficient in front of y is -1. Anytime you have a coefficient of 1 or -1, it's oftentimes best to use the substitution method. So if we rewrite this first equation and want to get y by itself, we could get 2x minus 10 equal to y. Okay, so if we would subtract 10 over to the other side and then add the y to the other side, we would get this. Now we have that y variable has a leading coefficient or a coefficient of 1 isolated by itself. So what we can do is take the second equation, and everywhere we have a y, we're going to replace that with 2x minus 10. So rather than write 4y, we're going to take 4 multiplied by 2x minus 10. Okay. The reason we do that, before we had two unknowns. We had x and y. Now we use the substitution method. We have one unknown variable. We have it just in terms of x, so now we can solve this. 6x plus 8x minus 40 equals 1. Combine like terms, 14x equal to, add 40 to the other side, 41. If we would divide by 14, we get x is equal to 41 over 14. Now we need to find the y variable. So if we look at our first equation, we already have y isolated by itself. So if we use that, we have 2 times the quantity of 41 over 14. 14 minus 10, and that's equal to y. So if we multiply this out, we get 41 over 7 minus 10 equals y. If we would get a common denominator, we would have to multiply by 7 over 7. So 41 over 7 minus 70 over 7 is equal to y. 40 minus 70, we get negative 29 over 7 equal to y. So we found our x variable, found our y variable. The solution to the system is the ordered pair. So our ordered pair would be 41 over 14 negative 29 over 7. Okay, so if we would graph these two equations, look for where they're intersecting on the graph, they would intersect at this coordinate, this ordered pair. In the next example, we have two equations where one of them is not linear. Okay, so we're still going to solve this system algebraically. Since we have both equations where y is isolated by itself, we could set those two expressions equal to each other. So if y equals 8x, we could set 8x equal to x squared plus 6x. Okay. You could think of this as the substitution method. In that first equation, I'm substituting an equal value for y, which is 8x, in for y. So we have 8x equal to x squared plus 6x. We would subtract 8x to the other side. Now we have 0 equal to x squared minus 2x. If we factor that on the right, we have 0 is equal to they have an x in common, so it's x times x minus 2. Now we would use the zero product property. So x equals 0, x equals 0, and x minus 2 equals 0. We would solve that, x equals 2. So our two solutions in this case would be x equals 0 and x equals 2. We should plug these in to make sure they work, especially when we don't have linear equations. If we plug 0 into the first equation, y equals 0. Into the second equation, y equals 0. If we would plug 2 into the first equation, 2 squared is 4, plus 6 times 2 is 12. 4 plus 12 would be 16. If we plug 2 into the second equation, 8 times 2 is 16. Okay, so both of these values work. You should always make sure and get in the habit of making sure to check that your solution works. So our ordered pairs in this case would be 0, 0. And our other one would be 2, 16. If we graph these equations, these would be the two locations where they intersect. In the next example, we want to use the elimination method, also known as linear combinations. When you're using linear combinations, it doesn't really matter which variable you use, x or y. It depends on the coefficients in front of the variables. If one is positive and one is negative, that's sometimes easier to use to try to get them to cancel out. So in this example, I'm going to eliminate the y variables because one's positive, one's negative. So if we look at 2 and negative 3, trying to find the least common multiple, which would be 6. So for the first equation, I'm going to multiply that by 3, and in the second equation, I'm going to multiply that one by 2 to get both of the coefficients in front of y to be 6, one positive 6, one negative 6. So if we multiply the first equation by 3, that would give us 9x plus 6y equal to 36. If we multiply the second equation by 2, we would get 8x minus 6y equal to 66. Now once we have this, we multiply them each by some value. Going to add them vertically. 9x plus 8x, 17x equal to positive 6, negative 6y. Those cancel out. 36 plus 66, 102. You divide x by 17. 102 divided by 17, x is equal to 6. So now we need to pick one of the equations. Doesn't matter if we pick the first equation or the second equation. Going to plug that x value in. So we get 3 times 6 plus 2y is equal to 12. 3 times 6 is 18. So if we subtract that to the other side, 12 minus 18 is negative 6. Divide by 2, y is equal to negative 3. So our solution, our ordered pair to this system would be 6, negative 3. Okay, should check, plug in 6 into each of those, and negative 3, make sure we get something that is true. Well, 3 times 6 is 18. 18 minus 6 would be 12, so the first equation works. 4 times 6 is 24. 24 plus 9 would be 33. So that solution works in both equations, so that means it is a solution to the system. In this problem, we want to solve a system. Doesn't matter which method we use, substitution, linear combinations, or graphing. I'm going to choose to use linear combinations because if I look at the coefficients in front of x, 3 and 6, and 2 and 4 in front of y, all we have to do is multiply the first equation by 2 to get some things to cancel out. So if we multiply the first equation by 2, we're going to get 6x plus 4y equal to 10. Our second equation we just have to leave. It's negative 6x minus 4y equal to 10. So if we look here, on the left, things are going to cancel out. We'll be left with 0 equals 20. We know that it's not a true statement. In this example, we would get no solution. Okay, so that means if we graph these two equations, they would never intersect. The lines on the graph would be parallel. And we know parallel lines will never cross, never intersect. That's why there's no solution to this system. We want to solve this system. We have 3x plus 6y equals negative 10 and 9x plus 18y equals negative 30. Okay, looking at these two equations, you should recognize that there's some similarities between the coefficients and constant in the first equation to the second equation. All we have to do is multiply the first equation by negative 3. And if we do that, many things are going to cancel out. Okay, so if we multiply that first equation by negative 3, we'll get negative 9x minus 18y equal to a positive 30. And then if we bring that second equation right below it, we have a positive 9x plus 18y equal to negative 30. We add these two equations together, negative 9x, 9x cancel out, negative 18y, positive 18y cancels out, so all we have is 0 on the left side, positive 30, negative 30, we get 0 equals 0. So if you get a number equal to a number, a variable equal to a variable, that means there are infinitely many solutions. Okay, so there's many different values we could put in to make this equation true. And if we would look at the graph of these equations, basically we would only see one graph because they lie on top of each other. So those graphs, if this occurs, are said to coincide. So a couple vocabulary terms. The graphs lie on top of each other, essentially it's the same equation, they coincide, which means there are infinitely many solutions. In this last problem, we're going to do an economics application problem, okay, referring to supply and demand. Mr. Johnson Manufacturing has determined that production and price of a new basketball shoe, similar to his classic Adidas Superstars, should be geared to the equilibrium point for this system of equations. Okay, so basic supply and demand graph. Our supply equation is going to be increasing positive slope. The demand function is going to be decreasing negative slope. What we're essentially trying to do is find where these two intersect. That's called the equilibrium point. In this problem, we have P equals 160 minus 5x. That's the equation representing the demand. Okay, we can tell it's a demand because it has a negative slope. It's going to be decreasing. P equals 35 plus 20x. That's going to be our supply curve. We know that's the supply curve because it has a positive slope. So what we're going to do is solve this system, find out where they're intersecting. That's the equilibrium point. Since they're both set equal to P, we could set these equations equal to each other. So 35 plus 20x is equal to 160 minus 5x. So if we subtract 35 to the right side, add 5x to the left side, we would get 25x equals 125 divided by 25. We get x is equal to 5. So in this case, x equals 5. That is selling millions of shoes. So that's how much supply we want. 5 million shoes, pairs of shoes. Now we want to find out what the cost would be, what the equilibrium price would be. So if we plug 5 in for x into the second equation, we get P is equal to 35 plus 20 times 5, which would be 100 plus 35, $135. So if we were going to graph this supply and demand curve, our ordered pair would be 5, 135. The 5 represents millions of pairs of shoes. The 135 represents the cost of the shoes.